No, don't worry. Scare everybody away. I should. Nicole, we need to remove some of the recordings from our account right now. It's too full.
I already did.
Already did? Okay, perfect. And we need to save one of the recording for Mr. Brooks' call.
Done.
Thank you very much. Irene, pleasure seeing you. Okay.
Yep.
Whoa.
Good morning, everybody.
Good morning.
Morning.
Hi, Irina.
Should we give it a minute and then start? Just make
Yeah.
anybody.
Yeah, we just hit 2 after. Yeah, I'm sure more people will be joining.
Yeah, I had an appointment in San Jose yesterday, and I wondered why there was nobody on the streets.
Oh,
I was
Juneteenth.
not even aware of the fact that it looks like it was a holiday, but yeah.
Yeah.
Okay, if we're so few people, we can make this interactive, I think.
We should, yeah, we'll start at 5 after maybe. But that would be great to be interactive. I'm sure there's gonna be lots of questions and clarifications, so that'll be great.
Mm-hmm.
It was nice meeting you in 3D, by the way, the other day, Axel.
Yeah, likewise.
It's so weird if you Zoom with someone, like since pandemic, if you Zoom with them for a few years, in my head, I'm like, have I met them in person or not? Sometimes it almost feels like you have, but yeah, I realized I hadn't met you in person until that.
Yeah.
I've experienced that phenomenon.
Yeah. Yeah, I had someone the other day on a personal level say, "Oh, great to meet you in person." I'm like, "Oh no, we've met before." It's like, "No, we haven't." It's all been through Zoom for 3 years.
Yeah.
Yeah. No, and people look kind of different enough in 3D where it's kind of like it's a little jarring at first, like but it can be. It doesn't have to be, but it can be.
Yeah. Yeah, not as jarring as the old days. Like if you ever listened to a particular radio show and knew the radio personalities, then you saw them in person, you're like, wait, no, that voice doesn't go with that body.
Yeah, exactly.
Yeah. Yeah.
Okay, so
Did we
10:05, and then I think we'll start because otherwise
we start? Yeah, we usually, yeah. And I know it's not lack of interest in the topic, so maybe people are just delayed in getting back from meetings. So let's kick it off.
I had a few people email me and tell me that they had conflicts, but that they wanted to see the recording. So.
Recording, yeah. Okay. All right.
good. Okay, then let's go.
Yeah, I'm very looking forward to this.
And I'll just preface just real quick. So I met Axel in 3D about a week ago at an event over in the East Bay, over in Berkeley, and Axel got the privilege of seeing Axel on a panel on AI and what it means to the future, and did an excellent job. So
thank you.
It's great being part of that.
Yep. Okay, good. Okay, I would say let's go because otherwise we won't be able to get through.
Yeah.
Okie dokie. So let's have a look. So I thought, we'll make it a little bit structured, but that of course also means that at any given point in time, you're welcome to ask questions if there's anything that's not quite clear. So let's go through it. I want to first say what really is artificial intelligence and how is it being separated today, and which parts exist. Then a general approach to AI, particularly generative AI. Then how you train it, and the AI training. What do you do with the input data? How do you filter? What do you do with that? Then a little bit of math with regards to Markov chains, and then have a little bit of an explanation as to how that maps directly onto the neurons and synapses in the CNN. Continue with a little bit of math and hardware with that, and then highlight a few of the existing software and frameworks for both training and inference.
When Axel, when you talk about the CNN, can you, if you can differentiate or correlate between deep CNN and CNN, please?
Yes,
Thank you.
I can, and we will get there. So yes.
Thank you.
And it makes it even more entertaining if you use the CNN, the news station, as a backdrop for any thinking about CNNs in this context.
Ooh. Yeah.
Sorry, I just had to inject some humor.
I love that. I love it. Thank you.
Yeah, it's very humorous, but there's actually no mapping between one CNN and the other CNN. But yeah,
I know. Yeah. Well, let's hope not. Yeah.
yeah. So in general, artificial intelligence consists of two parts, and they vastly differ on how they are implemented because the mathematical backgrounds for both vastly differ. And so today there is effectively training. It can be supervised, unsupervised. Then there is a version that relies on backpropagation, particularly of errors, annotation, back annotation, and reinforcement learning. That's basically the categories. There are many, many more, but these are the ones that have shown to work reasonably well and are in use today, all of them mathematically fairly computationally intensive. And then the inference part is the relatively simple one where you have already created the model in the background is being used, and then the model, in fact, is used to create the answer that came out of a question. And again, training part is mathematically vastly more complex. So when do we use AI and generative AI? And
Excellent.
Yes.
Sorry to interrupt. I wasn't sure if you're going to cover any more. Can you just go back to that slide for just a sec, if you wouldn't mind?
Yes.
Just on the annotation and back annotation, I think I understand what the other bullets are, but what does that mean, the annotation, back annotation?
So annotation would be a way by which a human would create a tag for a particular either text or a picture or an event, something that would allow an AI training instance to understand what's going on. And back annotation would be the same type of annotation when the learning has gone awry and something didn't quite work out the way, right?
Okay, so it's kind of like enriching. So enriching the data set perhaps is one way to think about that from what just the system would see on its own. You're actually, the annotation is adding in.
It's basically adding metadata to the
Gotcha.
existing data.
Okay.
So
All right.
what is the detail, Alex? It's adding what? Axel, it's adding, where do you add the annotations?
The annotation would be added in the metadata, and I'll come to all of that.
Okay.
Right?
Excellent. I can give a very quick example so people understand.
Yeah.
Think about a simple neural net that try to figure out handwritten digits. So you get the handwritten digits, and besides them, you have, let's say, if it's a zip code, you have the actual address. So the system does not try to figure out the address; it just tries to figure out the zip code. But you have the address, so you actually have metadata that tells you what the correct zip code is supposed to be, regardless of the handwritten. Yes?
Right.
You try to figure out handwritten, and you have metadata that is annotating the handwritten, tells you what it truly is.
Yes.
Axel, how is that different from a parameter?
The parameter would be in the net user data that the training instance would take in, whereas the annotation is a tag that is not directly part of the net user data, right? I'll come to that. I can explain that in a little bit more detail later, right?
Thanks.
So why do we use AI, and what are the approaches to do that? So generally, we try to use AI when there is a large enough input data set that describes a problem well enough so that we think we can solve it using statistical methods, but there's no way to deterministically do that, right? So in essence, we can't find an approach that is algorithmic. In that case, AI is being used because it is a useful approach to solve the problem, and it usually renders results with regards to probabilities, right? So let's say you have a system of equations, then usually you would look for something that deterministically says x is 3 and y is 4, and that's about it, right? That's what you care about in a system of linear equations. Now, if you've got no way to determine something and you just go for what is the likelihood of something being correct. Statement A is true, let's say, with an 80% probability, and false with a 15% probability, and unknown with a 5% probability, then using AI and statistical methods is a perfectly fine approach to solve a problem, right? Because ultimately, you're not looking for, x is 3 and y is 4. That's not what you're looking for. It doesn't have to be mathematically a correct outcome. You just look for likelihoods for something to be correct, right? And that's, of course, why AI and particularly vision and picture and image and even video analysis are so interrelated. And, you remember when I wrote the entire stuff in Verilog for building a CNN that was capable of extracting not only pictures, but also objects in the field of vision, because that's something that Tesla, as of today, even can't figure out, right? If you've got a tree that is somewhere next to a street, you want to, of course, avoid the tree. You don't want to crash into the tree, right? But if the sun projects the shadow of the tree onto the street, you have to understand that that is a shadow. You don't need to evade the shadow if you're a self-driving car, right? So you have to understand that this is a shadow of a tree and not the tree itself, right? That's, in fact, one of the reasons why Teslas, as of today, still crash into trucks that have toppled over on a highway, because clearly the vision analysis there isn't working properly and thinks that this is a sign that is hanging a little bit low, right? It also crashes into first responder vehicles because they are not supposed to be there, right? And so understanding the context and assigning a likelihood to something is a statistical method, and that's exactly what we need to use in AI and generative AI, right? So it's not a deterministic outcome, it's a probability. So how do we do that? Well, first of all, we got to find input data sets. And then, of course, we can say, well, we can use combinatorial logic and then create all of the possible, we could create basically the entire solution space, right? But that's, of course, way too big. Therefore, we just try to find an input data set that we can feed into an AI training instance. And then we make the AI the subject matter expert on that particular subject. And it will find the probabilities of pretty much everything that is included in that training data. And of course, the training data now becomes paramount, because a lot of people say, oh, the AI is such complex software and blah, blah. That's not the case. In fact, the AI software itself is actually quite, I wouldn't say trivial, but it's fairly simple. The software is computationally intensive, but the software itself is relatively easy, because all we really do is we find the probabilities of statements in the data set, in the input data set, and then use that to determine the probability of a certain thing or event or X data sample, right? So let's say we train AI on physics textbooks from before 1906, right? So from before Albert Einstein came up with the theory of relativity, right? Now, all of the answers will be effectively saying, hey, we've got Newtonian mechanics, right? And that's okay, because we may have trained it wrong. So at this point in time, that AI instance would not tell us that there's something beyond Newtonian physics and mechanics, because it fundamentally doesn't understand physics. It merely picks the most probable answer, and the most probable answer will be, of course, Newtonian physics, because that's what it was trained on, right? So we're not at a stage where AI understands anything. It just says, hey, from all the training data, 100 textbooks, and 100 textbooks say F is m times a, right? Force times mass. That's, mass times acceleration is my force, right? It doesn't say, well, that only applies for speeds way below the speed of light and all that kind of stuff, because again, the instance has been trained on Newtonian and therefore doesn't understand physics, and therefore cannot say that relativistic physics is the one that's actually correct, right? So how do we derive all of that? So in essence, if you train something today, you effectively make very, very large combinatorial logic cross correlations of Markov chains, right? And so Markov chains are basically a probability for something that you can compound. So let's say you have, you type a big capital I. Capital I could be followed by a whole bunch of things. Could be followed by an N, or an apostrophe M, or apostrophe double L, right? And all of these have different probabilities depending on the text you trained it on. And of course, they will even be different between, let's say, English and German, right? They will be very, very different. But in the end, you will receive, if you train the AI instance on something, you will receive a very large list of things that show up with their associated probabilities, right? So you can do that for words, you can do that for entire phrases, you can do that for paragraphs, and you can do that for entire books, right? And so if you do that, then you will be able to see what the probabilities are for each of those combinatorial things called Markov chains, right? And now, of course, the big computational problem is, what do you do with that, and how can you consolidate that into a coherent and consistent model? And that's in fact where all the math comes in, right? So again, if you look at, just the letters here, the probability of A, just in combinatorial logic, is just that. It's not, there's no secret to it. It's a probability of A showing up, right? And then if you do that for AB, it's a probability of A showing up multiplied by the probability of B showing up. And the same is true for ABC, right? So that's fairly straightforward and simple. But if you have an AI instance read a text, the probability is, of course, distributed along a statistic that is not just the probability of 1/26 of the alphabet. That's not how it works, right? We don't use every letter with the same probability, because ultimately a text is not a probabilistic combinatorial combination of Markov chains. That's not how it works, right? So now we basically say, okay, the probability of A showing up is in fact the probability of A in the alphabet multiplied by a weight, right? And so that's really the secret behind it. You have to find the weights in the distribution of the occurrence of each of the letters. And you can do that and can continue to do that. And so what you will see is that the number of weights you need just goes up and up and up. And the weights ultimately make up your model. And so this is a very, very simple model. I mean, you see, we're just looking at A, AB, and ABC, right? We're already dealing with 3 weights, right? Now, in real life, the LLMs, they use not, of course, only letters, they use words they look for. They look for entire paragraphs and entire articles or books. And the next generation of LLMs will be multimodal, so that will include pictures and videos. And so that's where, in fact, a good portion of the annotation comes in. If you look at any picture today, you usually have metadata already in the picture. So it will say when it was taken, where exactly it was taken, by whom it was taken, and that kind of stuff, right? And so that's already giving some incremental data that is metadata. So it's not the picture itself, but it's data that either the user created or that the camera created when the picture or the video was taken, right? So therefore, we have data that is not the net user data, it's metadata that is incremental to the data in the picture, right? And so metadata can always be added to anything. It doesn't make sense to, letters to add metadata to it, but to, let's say, a paragraph, because it might be an excerpt from a book or an excerpt from a patent or an excerpt from, whatever. It could be a poem, could be literally metadata describing anything that is giving additional information to the training instance that is tasked with extracting as much information as we can out of a particular piece of data and information and text, letters, whatever, right? Including pictures and videos, right? And so if we look at this, this is exactly what happens in a convolutional neural net. So we've got, I drew the smallest possible CNN. It's called a 3x3 kernel of a CNN. And if you look at it, each one of those neurons has a value indexed by INJ and a weight indexed by INJ, right? Now, if we have a look how this progresses, because you go through this multiple times, so the training data is effectively mapped onto the CNN. And what you now have is you go through the math and you have a look at what is the formula behind it. It's actually quite simple. The next iteration of your xij is the sum of all of the xij's multiplied with their weights for all of those around you, and then you add your own to it. So it's effectively a fused multiply add. And then you divide it by the sum of the weights, which normalizes the data so that you don't have a exponential growth of the values over the many, many steps you have to execute this, and then gets renormalized. And if you look at it, it's a very simple formula. It's really not much to it. And if you look at even just the math, really all you need is a multiply and an accumulate, right? And so that's why what we do today, fused multiply adds, have been used in high performance compute forever, right? And the normalization is just the sum of the weights. And so that's about as trivial as it gets. Well, from a mathematical standpoint. From a standpoint of how to implement that, it's very different, because if you look at each one of those values, guess what? Each one of them, the central neuron of your kernel, is also a neighbor to another central neuron. And so therefore, you have access conflicts. And so while this looks awfully trivial, it is not. You will have collisions to memory, because let's say the center one wants to access the one to the left at the same time as the one that I didn't draw here because I only drew the 3x3 kernels. But each one of them will have a conflicting access. And so that needs to be accounted for. And therefore, the hardware to do that isn't exactly quite trivial, right? So as I said, the math for it looks trivial. It's literally, it's fused, multiply, add, 9 times for each 3x3 kernel. But it creates access collisions all the time. But we already have the knowledge of how to do that. So vector and matrix math is usually part of the instruction set of a CPU today. So the math behind it and executing it is not the problem. The problem is that we have effectively contention to memory, because multiple of those central neurons will always have conflicting accesses to all of the other neurons around them, right? And so that's why the math looks trivial, but the implementation is not quite. So, I mean, really, if you look at it, each one of them, the Xij is always replaced by a new Xij for all of the fused multiply adds around its neighbors and itself. So you have to keep a copy of it, right? Divided then by the sum of the weights, right? And so that is the math behind all of the transformation of the Markov chains that we use as input into the model that ultimately becomes the expert system on the subject matter. Right? That's really it. There's not much more to it. It is just massive amounts of it, right? Massive amounts. It's bazillions of them. I mean, literally, it's, if you look at the GPT-3 was 175 billion input parameters, right? The problem with that is it effectively, if you look at all the neighbors and all of the operations it has to go through, if you go through all of the possible opportunities and possibilities, it's 175 billion factorial, right? So you have to thin it out a bit, because 175 billion factorial, that is not solvable, not in the lifetime of the universe. Even if every single atom in the universe would compute, it simply is not solvable. So therefore, we have to thin out the number of possibilities and then just compute those. And that's exactly what all the transforms are and what all the vector and the matrix and the tensor math is about. And so that's why today, everybody says, well, you have to go for something that is accelerated compute, because if you do what initially was tried to do all of that compute in a CPU with memory, that's not possible. There simply isn't enough computational horsepower. And on top of that, there simply isn't enough memory to store even the intermediate results. So what happened, about 15 years ago in high performance compute was, we came up with the concept of accelerated compute. So you've got a CPU and DRAM, and then all of the work is really done in the accelerators. And today they are mostly GPGPUs, and they have their own memory. And now you can spread it out over many, many GPGPUs. And today's GPGPUs, they all have lots and lots of render cores. And guess what they're doing? Fused multiply add, because that's really what a GPU does, right? So that's how it got spread out. And the newest NVIDIA GPGPUs, they've got 18,000 render cores on a single die. So now you can spread out, let's say you've got 4 of those, you can spread out your matrix math that you need, right? You have 72,000 render cores available to you to run this application just on 4 GPGPUs. And that's, of course, what made the big step ahead. And that's why GPT-3, 3 and 3.5, and now even GPT-4, we were able to create a model out of billions and billions of parameters, input parameters. Was completely impossible before. I mean, you couldn't build a CPU with enough cores to make that all work, right? It just simply didn't happen. It was impossible to do, right? So if we look at the software frameworks that we have today for training, we've got the TensorFlow, but that's more and more replaced by JAX. Even Google seems to transition away from TensorFlow. There's NumPy and PyTorch, both of them libraries for Python. And all of those rely on underlying math libraries. And for the most part, they are CUDA today. More and more are switching over to OpenACC and OpenCL, but we still have a very prevailing use of CUDA today. So that's what everybody uses for training. And you can see these are all high-level languages. So they themselves don't do any math on the CPU. They just farm it out through the math libraries onto GPGPUs, because again, on CPUs, it simply wouldn't be doable. For inference, I mean, I've played with a whole bunch of them. DAL-E, there's DAL-E ChatGPT, probably everybody has played with that at this point in time. And there's Midjourney, which is not too bad either. And Microsoft has Copilot. There are plenty of others, and they seem to pop up everywhere and die off 3 weeks later. I mean, I've tried a few of those that have already died, but I think the issue simply is ease of use is more important than the use of math, because that's being taken care of by CUDA and OpenACC anyway. And there are a new framework, very, very new framework coming up that that displace CUDA and even OpenACC. So there's a whole bunch of stuff going on. It's a very, very, very dynamic industry. And I mean, we're in the infancy, right? The first GPT-3 stuff, when did that came out? Came out like 18 or maybe 21 months ago, right? So considering the growth of this, I think it's pretty amazing that we already have this kind of ecosystem for all of AI, based on the fact that the issue of the training has been reasonably well solved. So that's pretty much it for the presentation. So I'd be more than happy to go into some of the math and some of the hardware that we are using, or any questions that you have. Happy to answer, and then we can go from there.
Axel, I usually have some questions or comments. It's my understanding that most standards, including OpenACC, will end up translated into CUDA when you run on NVIDIA accelerators.
So yes, for the most part, these math frameworks, they use whatever hardware is there to accelerate stuff, right? So OpenACC, yes, if OpenACC finds an instance of CUDA running, then it will use the GPGPUs. That's correct.
Yeah.
Mm-hmm.
We don't really have a low level. I mean, every hardware manufacturer has their own low level language, and it's not necessarily completely standard. It's only that if you use OpenCC, you can you don't need to care for it for the most parts.
Yes and no. To some degree, I mean, OpenACC and OpenCL were there before CUDA, and before that was Intel's MKL, the math kernel library, right?
Yeah.
So those all predate CUDA, but they were never very well documented. They never were used outside of the academic circles. And the problem was that even the HPC guys didn't use them, because in high-performance compute in the very beginning, you couldn't see that there was a performance benefit by using them. And so a good portion was, of course, that as soon as CUDA started being used in HPC, in high-performance compute, and all of the supercomputers that the Department of Energy has bought and put together and is using, as soon as CUDA started being used on a much broader scale and the performance benefits became clear, basically CUDA displaced everything else that was before. So in HPC, if you don't support CUDA today, then pretty much you're dead, despite the fact that CUDA itself uses another library under it called SYCL. So, right, SYCL.
A quick question. So where are these like CUDA and OpenACC, these math frameworks being developed? Where?
So OpenACC was initially developed at, I think it came out of CMU and Berkeley. And then it sort of was taken over, AMD took over, and therefore AMD is a big proponent of OpenACC. But again, the use case today would be, very limited because OpenACC had a bunch of drawbacks. And the drawbacks simply were it ran only on ATI GPUs, and they were not particularly general purpose, and they didn't provide the performance benefit that CUDA did later on NVIDIA GPUs, right? And so the problem, of course, was that all of the academic approaches pretty much went away after CUDA became commercially successful, and CUDA is, in fact, the biggest lock-in for NVIDIA, because very simply, once you write software, you don't rewrite it again, right? So you have, let's say, you've done all of your rewrite of software from old Fortran into new C++, and you've rewritten everything, and you're using CUDA. These guys are not going to change, and they're not going to, rewrite it again towards another framework. That's just not going to happen, right? So CUDA, despite the fact that it never was standardized by a standards body, has become the de facto standard for pretty much everything in AI as the underlying math library. And in HPC, it has been for, I would say, 15 years now.
But if there were going to be other advancements in math models or like for future use, are they going to come out of universities essentially, or where? I mean, because that seems like it's one of the sort of bottlenecks, or needs to be an area of innovation, not only on the chip at the the chip side of things, but also the underlying math models. And
yeah, so nothing precludes anybody from writing yet another thing that runs under CUDA, replacing SYCL, even if it has direct hardware function calls, right? Because CUDA really is a math library, right? The same way that Intel's MKL was a math kernel library. The problem was just nobody knew about the Intel MKL, and believe me, I compiled plenty of stuff towards it, and it was pretty buggy in the beginning, right? They fixed it, but it took NVIDIA over $10 billion to get to a point where they are today with CUDA, right? And so today it's a fairly robust library. It has all of the function calls that you would ever want, and so I'm predicting that. Unless there are vastly more statistical functions needed that currently are not part of CUDA, OpenACC, OpenCL will continue to wither away, and everybody will use CUDA. And in fact, we have a CUDA translation layer in our hardware. We can execute CUDA commands and then convert that over to native commands on our accelerators.
If I may add to this, and Axel, correct me if I'm wrong on this one. NVIDIA hardware topology and their integration in memory. One of the key time delay in processing of any mathematical model is how fast you can fetch information from memory back into your GPU and back and forth. So the design of CUDA and the GPUs, or CUDA currently supports a very specific integration model that allow very fast fetching of data from memory back into the GPU to process and put it back in. And over time, this type of integration creates, I call it a deadlock to the provider. I don't see NVIDIA going out of business for the next very, very long run. I think the next thing that may threaten NVIDIA would be, because of that, would be quantum computers, and it might be that NVIDIA will come with that as well to make sure that they have future. But otherwise, when it comes to GPUs, CUDA is in very strong control in this world right now.
Yes, absolutely. That's absolutely correct. But if you look here at the schematics for our training, right, you will see that very simply the CPU and DRAM model didn't work. And so we're starting to see that the CPU and GPU model starts to fail because very simply the problems are too big, right? So if you look at the arrows here, so this arrow is, in reality, is a lot thinner than this, right? This arrow is also a lot thinner in reality than I drew it here. This arrow is pretty thick.
Very thick.
Right?
Yeah.
What's missing is a way to connect multiple GPUs together, right? So today, if you're good with 18,000 cores, you're good, because then that fits onto a single GPU, right? But if your model requires hundreds of thousands of GPU cores, well, guess what? You now have to go from this GPU through a fairly thin arrow here to the CPU and then out to another CPU, so that that one can be spread out to another GPU, right? So what I didn't draw here was what we are doing, which is heterogeneous accelerated compute on a larger scale out factor, right? So NVIDIA sort of went for an interim solution by inventing something they call NVLink. So they are now able to connect up to 4 GPUs with a link that is not PCIe, right? And yes, you can do that. So the max they can grow to at this point in time, and even that has very high latency, is 72,000 render cores. That's a fairly big machine, but it's not hundreds of thousands of cores. And because of the fact that there's no easy way to share the data that may reside on the video DRAM, on the video RAM of a GPU through the NVLink, the scale out is limited. So for anything that looks like a typical finite element method, or anything like this, where you have all of the communication between each one of those cores, you will see a performance degradation. So 4 GPUs give you about 1.7 times the performance of one, but you still have 4 times the power consumption of one, right?
Yes.
So that is not a very good scale out. And the problem is that you can't get around to this. So that's why we believe, of course, yes, there is a next generation of stuff that is a much better accelerator for this kind of math, right? And this applies to vector and matrix and tensor math, right? It's the same. What you do is you multiply a number of elements, whether in a circle or whether in a row and column, but you multiply elements. And the larger the row and column and the kernels are, the more issue you have with access to memory and with the scale out, right?
Power.
And well, of course, power is part of it, right? Because again, you have 4 GPUs in it, and you have 4 times the power consumption, but 1.7 times the performance out of it, right? So that's not a very good growth. And in fact, if you now have to go to 8 GPUs, you now have to do everything through the CPU and then out, not to DRAM, because DRAM can't be shared across CPUs today. There's no CC NUMA switch anymore. You can't find them anymore. So now you have to go out from your CPU to a network interface card, to a top of the rack switch, out to another CPU, and then to another accelerator that is a GPU or another special purpose accelerator, right? And so the problem is, once you go past 4 GPUs, you're really screwed, right? And granted, 72,000 render cores is an enormous amount of compute. But if you look at, a trillion parameter input model for GPT-4, then you can imagine even 72,000 cores will not be helping you much, right? You need many, many more than that for a trillion parameters, right?
And the problem is both time and power.
That's correct.
That's
correct.
Yeah.
That's correct. That's exactly the problem, right? So if your model fits onto 1, 2, 3, or 4 GPUs, yeah, today that's a very good solution. There's not really much need to go beyond that if you can squeeze your model or the model generation onto that, right? Meaning all of your matrices have to be such that an N by M kernel can fix it, right? If you can't, then, well, it gets very expensive very quickly. And not only from the standpoint of buying GPUs, but also your power consumption and the time it takes to do it all, right? I mean, the rumor is that GPT 3.5 took close to 6 months on over 10,000 GPGPUs, right? And these GPGPUs are not exactly low power, right? Today, they are at about 400 watts, right? The next generation that's coming out is at 1,300 watts, right? So 3 of them are over 5 kilo, 4 of them are over 5 kilowatts. And that's just the GPUs. That's not counting the memory. And that's not counting the CPU that ultimately becomes the arbiter of the workloads. Right? So yeah, this is going to be a lot of power, right? Amazon just bought a data center next to a nuclear power station that provides 960 megawatts of power just for the data center, right?
Yeah, the number one problem that we have right now is that we cannot switch enough power on our grid towards those data centers. So the only solution is to have data centers and power plants commingled. That's the only
right.
solution that exists right now.
That's right. You know, and if for as long as it's at least a nuclear power station, you don't have CO2 generation. But think about all of that, right? And I can tell you that, you know, when Hurricane built their data center here in Fremont, right? They wanted really 30 megawatts, but they couldn't only get I think they could only get 24 megawatts. And they're like, okay, fine, 24 is fine, right? So 24 megawatts I think they built it in 2002 or 3, right?
Yeah.
So we went from 24 megawatts in about 20 years to 960 megawatts per data center. We can't continue that growth. I mean, that's impossible. So we got to get to some point where there's a better solution that doesn't quite burn that much power, right? But it's all boils down to this very simple CNN. That's what it looks like. It's, 9 neurons and 8 synapses. That's all it takes, right? That's the smallest kernel, of course, and you can increase the kernel size, and you have to for larger problems. But that's really all the basis for all of it, right? And again, if you look at the math terms, it's all well-known math. It's fuse, multiply, add. We've done that for 30 years in CPUs and in coprocessors, right? So that's really, from a math standpoint, not a big deal. From an implementation standpoint, in a chip it is, because you've got conflicting accesses all the time, right? And so that's part of the problem. And that's why, in fact, this looks simple, but it's not. The implementation is not, right? And so the math is trivial. Implementation is not. Right? Good. Any other questions?
Well, if you allow me to rain a little bit on the parade. First of all, Axel, thank you so much for explaining it. Even
Sure.
I could understand the basics. And I understand better what it is about and what kind of obstacles to its development exist. But my question is slightly different. My question is, how does it impact a normal person's life? Because what I am seeing at this point, and it's not necessarily everybody else's picture, is that I am being shoved some kind of AI in every single product I use for my work. Adobe wants to make me use some kind of AI. Microsoft tries to peddle some AI and everything else. And what I'm looking at is the situation where, okay, there is this powerful tool, AI, which I have no direct access to, and which is kind of being used against me in some way, because I am pushed to use whatever was done for me as an AI tool, and I have no idea how it works, how to apply it. All I see is that I'm being flooded with some kind of need for change, and I don't know what to do about it.
Well, so multiple things. First of all, if everybody stopped using the term AI, you usually would not object to the use of AI because it's invisible to you, right? So the thing that annoys me about Adobe is there's a whole bunch of things that annoy me about Adobe, but even if you have no pre-existing bias against Adobe, what they have invented with this new AI assistant is actually pretty good. If you use the AI assistant in Adobe in the reader, it will automatically create a summary of the document that you're reading, and it's pretty good. It's actually, believe it or not, the AI output that creates a synopsis of a document you're reading is pretty good. And if you can't comprehend it, it usually means that the entire article is either self-contradictory or written in a way that doesn't allow even an AI instance to extract the underlying meaning of it, right? So I use it all the time. I think it's actually pretty neat. Not that I like Adobe, but you know, the AI assistant in Adobe in the reader is pretty damn good, right?
If I may interrupt, I'm looking for a way to shut it up completely and forever, because I never am looking for a summary. I am looking for details in the documents. And AI assistant cannot help with that.
It could.
But,
you can train it. You can train it to do that. It will find it, but that's a different story. It's a very different story, right?
well, exactly. And that's my point, because I would like to use this powerful tool for my purposes, but I don't have direct access to it. I cannot use it in a way I use Excel, when I can write whatever formula I need to use, and bingo, it does whatever calculations for me that I need. So I have to rely on someone else to create some kind of AI empowered tool for me. And I've done several software projects, and not a single one worked.
Well, okay, so there are multiple things that come together. One is, as I said, AI, the software for AI is actually quite trivial, both on the training side and the inference side, right? So that's not a big deal. That's not a huge problem. The issue is that you will need to provide the training data. You would have to have the training data. And in your case, it would be the opposite of what Adobe does. So you want to have the details, only the details, and not the big picture, right? But again, even then, the training, the software for training, it is fairly trivial. It's fairly straightforward. It's not a big deal, right? So you need to differentiate in between the AI software and the training data that was used to do something. And again, theoretically, you can do it, right? And you know, I'm not saying AI does everything right and everything is perfectly fine with AI. There are certainly issues with AI, and you know, what I have an issue with is very simply all of the first iterations of OpenAI scraped contents from all kinds of websites free of charge, right? They don't pay license fees and royalties. Alex, what's up?
No, Axel, please finish your thought. Yeah, I was just going to piggyback off of your comments.
Okay. Yeah. So the use of AI is effectively up to us, right? What we all do. There are privacy issues, of course. There are issues around the unlicensed use of data, but I'm pretty sure that we'll figure all of that out. I mean, you know, the data that has been scraped from websites, okay, at some point in time, OpenAI will have to pay all of those publishers where they scrape the data, right? And that hasn't happened yet, but I'm pretty sure, I mean, the New York Times and Wall Street Journal, they already have settled with OpenAI. I hope all of the other providers will. And so you need to distinguish between, you know, what is the AI capability, what is the software that is used for AI, and how has the data been acquired? And if, you know, if OpenAI had acquired the data legally, I would have said, great, wonderful, right? It's a tool. But then again, you know, a lot of people don't want to see it in an unbiased fashion. To me, AI is a tool like any other tool, right? And I can tell you that we've used it internally and the results are not bad. So for example, whenever I get a new intern, right, the first thing I say is, okay, please write the Verilog for a register stack, and you can choose and pick, you know, if you want to do that with the top of the stack with a pointer or the top of the stack and a copy mechanism that copies it all around. And so most interns go for, you know, the top of the stack pointer, then they create the Verilog, I see it. And so I did the same with ChatGPT and said, ChatGPT, please write a register stack, 16 deep, 64-bit wide, and you know, try to use a top of stack pointer. And guess what? That code was pretty damn close to what all of the interns have done over the last 15 years, right? So it's not bad. It's not the best code ever that was created, but it's a good starting point, right? So you can use AI to help you do certain things. And, you know, even if it's just a starting point, it doesn't have to be perfect. You can always add something to it. And sometimes it's even in the question to ChatGPT itself, where you didn't completely disclose what you really wanted to do, right? But that comes back to you, and now it's like, okay, I forgot to specify that, right? But I think there's nothing wrong with it, because ultimately you can use it, you can choose to use it, you can choose to not use it. The problem is if you choose to not use it, other people who use it will be very much more effective and efficient than you, right? And so that's why we are using it, because ultimately, if it takes away routine tasks, guess what? Everybody, at least in my company, will be more productive. And that's what we're using as a starting point, right?
Axel, I'm sorry, my point was a little bit different. I'd love to use it. The problem is I cannot use it directly. I'm currently working with a kid in Texas. Well, I call him kid, he is probably in his mid-20s, who has created an AI model to analyze bank statements.
Mm-hmm.
And that's what I would like to have. That's what I would like to use, but I cannot create it myself. I always need to have some kind of an intermediary. And it's difficult to work with intermediaries, especially if you are talking about creating a tool.
Well, I agree, but the issue is that either you learn it yourself or you have somebody who does it for you, right? And that's been the case for all kinds of businesses for a very long time. Right?
Well, but to use Excel, you don't really need to know much math or anything else. I mean, it's a simple thing.
Yeah, but you have to learn Excel, right? So Excel itself is a tool, right? And
Oh.
again, any tool you have to learn how to use it. And, you know, ChatGPT actually makes it fairly simple these days.
Okay, I guess I need to try using ChatGPT.
Yeah, try it out. You'd be surprised. Alex, what's up?
Yeah. No, thank you. So far, so good. Lots of food for thought. I guess to piggyback off Irina's question, yeah, I mean, I understand her point about intermediaries. I mean, we have to, even Excel is made by Microsoft, right? So I wish, you know, I guess if I could and wanted to write my own, you know, ledger, kind of computational ledger kind of piece of software, then I could forego dealing with Microsoft. But that our whole economy is based on this kind of, you know, somebody makes the tool, we use it, we pay them for it, and you know, it's kind of a barter system of skills and technologies, right? So, yeah, so I don't know that that's avoidable. I mean, people run their own LLMs locally. You can do that. I mean, but that again, like Excel said, requires you to learn a lot of things. And then where is that tipping point where it's worth your time to learn enough of this stuff to where you can actually use it in a real business use case, right? I mean, that's what the question some of my clients are asking. What should I do with, you know, the creative agencies, the consultants, they want to use, Gemini, Bard, Dolly, ChatGPT, but they're just, first of all, we tell them, I don't know, I mean, this is as far as we've gotten. We tell them to buy a commercial license and read the terms and conditions before they do anything. That we tell them that's a minimum starting point.
Mhm.
And then take whatever the languages in the terms and conditions and disclaimers or lack of clarity, whatever, and take that all that stuff and then pass it on, put it in your MSA with your clients, because you're essentially going to use your client data as part of the use of these tools.
Mhm.
And that's kind of as far as we've gotten with it. Yeah. So
no, I think you're bringing up a valid point, right? And see, I understand Irina's point, but I think you're constraining yourself too much, because ultimately you can use AI to write a new software that in fact would extract all the data that you want, right? And believe it or not, it's not that difficult to do certain things, right? And particularly the software it writes might be much easier to create using AI than as if you have to write something from scratch, right? You can use the AI generated code as a starting point and then go from there. And what we found is, as I said, it creates reasonably good Verilog. I mean, it's not Verilog, that somebody who's done that for 25 years would write, but it's more than good enough as a starting point for somebody who's a novice and can get going. And the same is true for anything that it creates. It can create output in C++ that you can now compile towards whatever you want, right? And then you could run that software and have that done. Because ultimately, see, what you're doing is a very, very special application, right? And so the input data you would need to train an AI instance to create a model is very likely fairly limited, right? And if you do that, you don't need 10,000 GPUs to create the model. In your case, maybe one GPU would be good enough. You create the model, and all of a sudden you have the tool that you wanted that can extract the relevant info from all of the bank transactions. It might be a very simple one. I mean, I haven't looked at it, but theoretically, I can envision that this is a fairly low effort model to create, and it doesn't need to be artificial general intelligence. What you're looking for is a very, very small, limited scope foundational model for extracting financial information, right? It could very well be that it takes very little. I don't know. I haven't had a look into it. I haven't had a look into what the complexities of bank statements are, but in general, if you use it as a tool, it might be the tool that you need. And, you don't even have to write anything else on top of it. Could very well be. So if you've got somebody who does it as a service provider in Texas, what's wrong with that, right? That's the way it is. I mean, you don't generate your own electricity at home either, right? And you haven't hand soldered your cable modem either that connects you to the internet, right? These are all things that you buy either as a device or as a service, right? And the same is true for any kind of AI-generated software that helps you do your job easier. It's a tool. AI is a tool.
I understand that. I wish I could do it myself. I wish I could use the ChatGPT to create a code, implement this code, buy whatever GPU I need, and so on. I wanted, for example, to use AI tool to sort through multiple documents. How difficult could it be, for example, to recognize a tax return? Not very difficult. I mean, the forms do not change all that much, and so on and so forth. And my kid told me, well, if you give me enough material to train it, I'll do it. And here we ran into the issue of personal identifiable information,
right,
and got stuck.
Right. So either you have to have somebody who adheres to the PII safekeeping, or you have to do it yourself, right? I mean, there's really not much else you can do. That's just the way it is.
Yeah, I understand that. It's just life becomes more and more complex every day.
Well, yeah, it does. It does. That's the way it works.
Yes.
That's why we have more and more specialization, right, Chris?
Yeah, kind of pivoting off a little bit of what Irina said. She triggered a thought. In that she said she wished she could do it herself. What is your assessment, and Alex and Axel, probably both of you, assessment on a layperson like myself? I'm not overly technical, using ChatGPT or one of the other engines to generate code that I wouldn't know how to code myself to do a task like maybe Irina's saying. So could I use AI to then utter what I want done? Code comes from it, because I understand these things can do some level of, or produce some level of code, and then I might be able to run it myself. Like, what's the viability of that?
I'd say you spend 3 months on it and you have it.
Really?
Yeah.
So it's really not, yeah, okay. It's really not practical for a layperson.
Chris, what would be the end product you're aiming for?
Oh, well, part of this is, okay, and maybe a better example would be, like on one of my business endeavors, me and a partner are using Canva, and there's a lot of stuff we can do for our website with Canva. It's actually pretty cool. There are things that I would like to do that if I knew more in HTML, I would just do myself to kind of augment some of the features. And I was just understanding that code generation is one of the products that you can use an AI engine for. So as a layperson, what I was wondering is, instead of me figuring out how to code that widget I wanted, how viable is it, or practical is it for me to try to have an engine spit that out for me and then use that code in my web page or whatever?
So, I mean, it really depends, right? If it's something you don't have to compile, if it's some executable, then even if it's interpreted code, I would say it probably 2-3 weeks you can get there, right? If it's something where you have to have compiled code and then you have to learn how to use a compiler and create the software and this and that, that's a different story. But if it's interpreted code, it might be 2 weeks. I mean, there are people who do some prompt engineering, and believe it or not, some things take 10-15 minutes. I mean, I told you, we created the Verilog. I created the Verilog just to see what ChatGPT creates, just to compare it to, what all of the interns have done over the past 15 years. And that took me 30 minutes.
Yeah.
Right.
Because you know what you're doing. So that my proviso of saying a layperson is where the catch is in that. So if someone who knows what they're doing can use it as an accelerator, maybe on low-hanging fruit.
Yeah, I had an engineer at Google, as a friend of ours, who said that he uses their internal, I guess it's some internal version of Gemini or something, but he said they have to use that, but he uses it to help with augmenting and writing code a lot. Those is verbatim what he said. So, but that probably looks a little, but yeah, I've heard of a lot of people doing that. I don't think that's hyperbole at this point. So, by the way, Chris, I know a web developer who works with Canva. So if you needed a little bit of help, she's in Bait. So.
Okay, cool. No, thank you. I may take you up on that.
Okay.
Cool.
Do we still need a presentation, or, because I mean, if you've got any more questions with regards to what I presented, that's fine. If not, then, I can close this.
Yeah, you can close it. Yeah.
We can probably stop the recording too.
Yeah. Let me do that.